Hello. In this video we are going to talk about experimental determination of the Fourier coefficients of a square wave, and particularly we will discuss the philosophy or the overview of the experimental setup that we perform in our lab. So this is an overview of the method. Details we will deal in different separate video segments. Okay. Suppose I have a signal generator and then a filter and then a measuring device. This can be an oscilloscope. So we can use these three components to determine the Fourier coefficients of a square wave. So what we will do, we will generate a square wave out from the signal generator, and then we need a tunable filter. The purpose of this filter is to block certain frequencies and pass certain frequencies out from here. And then this measuring device, this oscilloscope, can measure the amplitude of the frequency which is passed through this filter. So as we know that this square wave can be broken into many sinusoids. This is the first harmonic, plus we will have some third harmonics, okay, and fifth, seventh, all odd harmonics. Now what we can do, suppose we can tune this filter and adjust which frequencies are allowed to pass and which frequencies are not allowed. Then if the fundamental frequency of this square wave is f, then definitely the frequency of this fundamental sine wave is f. This third harmonics frequency is 3f, then next will be 5f, 7f, etc. Now I will tune this filter so that it passes only the frequency of f, and all other frequencies 3f, 5f, 7f, etc. is blocked. Okay, so then only this first harmonics will be passed, and I can measure the amplitude using this oscilloscope, and that amplitude will tell me how much of first harmonics is present. Then I will tune this tunable knob and say I will set it to a different position so that only third harmonics is passed. So then in that case we will have only the third harmonics out in this oscilloscope. In the previous case we had the first harmonics, now we have only the third harmonics, and again we can measure the amplitude, this amplitude, and that will tell me the coefficient of this of the third harmonics in this square wave. Then I will tune it to a different position so that only fifth harmonics is allowed to pass, and so that will be a more higher frequency signal, and I can measure its amplitude. That will give me the coefficient for fifth harmonics. That's as simple as that. But in our experiment we have a twist. So our experiment is a bit twisted, complicated, because we do not have, or we do not use a tunable filter. So we do not have a filter whose cutoff frequency, or the frequency that it passes, it allows to pass, that's not tunable, that's not changeable. We have, or we use a filter whose cutoff frequency, or the frequency that it passes, is constant. So this filter can, say for example, pass only 15 kilohertz, but that value 15 kilohertz cannot be adjusted and changed to, say something like 45 kilohertz or here 75 kilohertz. So that's not possible. So we cannot change the this filter's cutoff frequency or passband frequency. So what's the solution? Okay, so I will rather, before coming to this, I will just tell you a small story which may help you in finding the solution to this problem. Okay. And the story is as follows. Suppose there is a group of boys or girls or students. They are of different ages, and the age range, say, varies from 1 to 5 years. So they can be 1 year old, 2 years old, or 3, 4, or 5 years old. And say there are 100 students. Now what I want to know is this: how many students are 1 year old, how many students are 2 years old, and so on, and how many students are 5 years old. To get the answer, I cannot ask the students about their age. That's that's the riddle, that's the puzzle I impose. So I cannot ask them how old are you. What I can do is rather observe when they get admitted into school. And we know that the students can be admitted only at the age of 5. So students below the age of 5 are not allowed in school. So this is the only information I can, or only thing that I can observe, and from that I have to count how many of them are of age 1 year, 2 year, 3, 4, or 5 years. So what can I do? I will say this is 2018. So I will see how many boys are admitted. Say there are 10 boys admitted this year. That means there are 10 boys of age 5. Okay, so now I know that how many boys are of age 5. Next question is how many boys are of age 4 or 3 or 2 or 1, so on. But this is the only thing that I can observe, that when they get admitted in school. So I can find the boys who are of the specific age of 5 years, but I cannot distinguish between the boys who are at age 2 years or 3 years or 1 year, because none of them get the admission in school. So what is the solution? The solution is nothing but to wait up to 2019, when some more boys will get admitted, say 20 boys get admitted. So that means there are 20 boys of age 4 in 2018. So those who are of age 2000 and of age 4 today, they will get admitted next year. So I have to wait till the next year to know how many boys are of age 4 today. Similarly, I have to wait till 2020 to see how many boys are admitted, and if there are 30 boys getting admitted in 2020, that means today in 2018 there are 30 boys of age 3. So that's the idea. So because I can only identify the boys who are of age 5 and cannot distinguish between boys of age 4, 3, 2 and 1, I have no other choice than waiting for a few more years, and every year I identify few more boys of a specific age. Okay, that's one story. Another similar story is as follows. Suppose I have a set of metal balls, a set of small metal balls of different diameters, like maybe this is 1 millimeter diameter, this is 2 millimeter diameters, then there may be some 4 millimeter diameter balls, and maybe so on, maybe 3, etc. So 1, 1, 2, 2, 4, 4, 4, 3, all these different balls are there. So all these metal balls, and they are all mixed, they are all in a common container. Okay, so the task here is again to separate the balls of different diameters. So what do I need? Definitely what I need is a filter. So I need a filter which has holes in it with a specific diameter, and only balls, those fit this hole, they can pass, and no other balls can pass. So using this filter I can separate balls of different diameters. But here is the twist. But I have only one filter, say with holes of diameter maybe 4 mm, okay, or maybe slightly less than 4 mm, slightly less than 4 mm. So if I use this filter, then these 4 mm balls will be blocked, everything else will flow through it, so I can separate these 4 mm balls. But then how do I separate 1 mm, 2 mm and 3 mm balls? The solution is, after separating 4 mm balls, heat up, give some heat to the remaining balls so that they expand, they grow due to heat, due to increase of temperature, remaining balls. So now what will happen, that this 3 mm ball will grow and become of diameter 4 mm, so this will be blocked next time, but 1 and 2 mm balls can be passed. Now after getting these 3 mm balls separated, do the same thing again, heat up the remaining balls which are 1 mm or 2 mm diameter, heat them up so that this 2 mm ball grows to a diameter of 4 mm, and then you can separate 1 mm and 2 mm balls. So heating is the solution. Heat them until they grow. Hypothetically, if you can heat them so much so that they grow to that much diameter. Okay, that's the solution. So now we will use the same trick for our square wave problem. What we will do is this. So we will have this signal generator, SG signal generator, then a filter, but it's not tunable. This is a constant frequency filter, constant frequency. Okay, and then measuring device. This can be a oscilloscope or DSO, CRO or DSO. Okay, so what I will do, I will, if possible, I have a signal generator actually which can be tuned. So I can change the frequency of this signal generator. So suppose now I have this filter which passes, say, only something like 15 kilohertz. So this point is 15 kilohertz. So it passes only 15 kilohertz signal from the input to output, and all other frequencies are blocked. Then what I will do, I'll first generate a square wave of 15 kilohertz. So this is 15 kilohertz. Then that means this is a composition of signals like 15 kilohertz plus third harmonics, which will be 45 kilohertz, fifth harmonics 75 kilohertz, and so on. But when it passes through this filter, only 15 kilohertz can pass. All these will be blocked. So here I will have only the 15 kilohertz signal coming to this oscilloscope, and I can measure the amplitude of this signal, which is in this case is the fundamental or first harmonics of this of the square wave. So first harmonics is known. Next, what I will do, since I cannot change the frequency of this filter, I will rather change the frequency of this signal generator and make it, say, of lower frequency, something like 5 kilohertz. So now if it is 5 kilohertz, that means it is a composition of a 5 kilohertz sinusoid plus third harmonics means 15 kilohertz, then fifth harmonics means 25 kilohertz, and so on. So it's a composition of all these different frequencies. Now what will happen? Through this filter, only 15 kilohertz, which is nothing but the third harmonics in this case, can pass. So once again 15 kilohertz, same frequency will pass, but here it is the third harmonics. And now I can measure the amplitude in the CRO here again, and then I know the amount of third harmonics. Similarly, next time what I will do, I will change this frequency to, say, 3 kilohertz, because if I make it 3 kilohertz, then its components will be 3 kilohertz plus 3 into 3 is 9 kilohertz plus 15 kilohertz plus then 7, that means so 21 kilohertz, etc. Now once again only this one will be allowed to pass, everything else will be blocked, but in this case this is the fifth harmonics. so I can measure the fifth harmonics. That's the philosophy of this experiment, and the reason or the fundamental assumption that we make here, due to which we can apply this trick, instead of changing the filter, change this signal generator's frequency. The reason behind this, why we can do it, is as follows, which is the ratio of, or the proportions, you can say the proportions of different frequencies, like proportions or ratios of different harmonics in a square wave is always same, no matter whatever is the frequency. So what I mean by this is that if this signal has a Fourier series like, let me write it here. If this is like C1 e to the power j omega, where omega now corresponds to 15 kilohertz, j omega t, plus C3 e to the power j3 omega t, plus C5 e to the power j5 omega t, plus so on. If this is the Fourier coefficients of this signal, then for this signal, which is again a square wave but of a different frequency, here its Fourier coefficients will be same, C1 e to the power j omega, let me call it omega 2t, plus C2, not C2, C3 e to the power j3 omega 2t, plus C5 e to the power j5 omega 2t, plus so on. So what is different between these two signals is this fundamental frequency. Here it's omega, here it's omega 2, but these coefficients are same. Here C1, here C1, here C3, C3, C5, C5. So that's the fundamental reason why we can change the signal generator's frequency instead of the filter's frequency in this experiment.